Okay, in this lecture, let's summarize the equations we've learned so far in special relativity. We have the relativistic form of momentum, p, which is gamma mu, where u is the velocity of the particle. P is a vector, a three-dimensional vector, so it has components x, y, and z. Gamma, remember, is shorthand. Gamma is shorthand for 1 over square root, let's see, 1 minus u squared over c squared in this case. Then we have the kinetic energy of a particle, which in relativity is gamma minus 1 mc squared. We have the total energy of the particle, which is just gamma mc squared. And that's the sum of kinetic plus E naught, where E naught is considered the rest mass energy mc squared. Basically, that's the part of Einstein's equation that everyone remembers, but the full form is gamma mc squared. We also learned an expression that was essentially a Lorentz invariant. I've written it in terms of the total energy squared, which is momentum times the speed of light squared, plus m squared c to the fourth. Of course, it's the m squared c to the fourth, which is invariant from one frame to the next. But written this way, the total energy squared is like the hypotenuse squared of a triangle, where one leg has length momentum times the speed of light, and the other leg has the dimension or length of the rest mass energy, mc squared. We learned some shorthands, right? The factor gamma, the Lorentz factor gamma, is just this total energy here divided by mc squared. So E over mc squared is a quick way to get gamma. And then we can use the Greek letter beta to represent v over c, or for the cases where I used u for the velocity, u over c. It's a dimensionless form of the velocity in terms of the speed of light. That's just pc over e. So the momentum times speed of light over e, and that's how you can calculate beta quickly. And gamma in that case, if I write it up in the top here, can be written then as 1 over square root 1 minus beta squared in that case. Okay, those are the equations we've learned to date. Let me just point out one example or one fact about this equation here that involves the rest mass energy squared. Let's talk about massless particles. For a particle without mass, then m squared c to the fourth would be 0. And that has to equal e squared minus p squared c squared by that equation we just had on the previous slide. That is true if E equals pc. In other words, for a massless particle, its total energy is just its total momentum times the speed of light. All right? So very compact. However, on that list of equations I had on the first slide, the total energy of an object is gamma mc squared. Moreover, momentum times the speed of light is gamma mu, the relativistic definition of momentum, times c. Well, if E equals pc, how do these two equations equate? They could only equate if u equals c, right? So if I take this u in the second equation equals c, I have gamma mc squared on one side and gamma mc squared on the other. Of course, in that case, the m's would cancel, right? So I don't have to worry about the mass being 0 in that case. So what can I conclude from this? What I can conclude is that massless particles must travel at the speed of light. Interesting. If you have no mass, you must be moving at the speed of light. Or vice versa. If you want to travel at the speed of light, requires, or if an object is to travel at the speed of light, it requires that object to have no mass. If not, if it had a finite mass, it would take infinite energy to reach that speed. Why? Well, our formula for the total energy is gamma mc squared. So that's mc squared over square root 1 minus u squared over c squared. If we let the speed u go to the speed of light, this is going to be 1 minus 1, so in the denominator is going to be 0. And so 1 over 0 is going to approach infinity. So it would actually take an infinite amount of energy to reach the speed of light. So much for those warp drive engines we hear about in science fiction shows. Okay, so that was just an aside about massless particles. Let's now see and learn a bit how we start to apply Einstein's equations of relativity. How do we do physics? First, let's review the conservation laws. What have we learned back in Physics 1 of Introductory Physics? We learned that momentum is always conserved for interactions with no external force acting on them. So if it's in isolation. And that's the same, that fact that we learned in Newtonian mechanics is the same as what we use here in relativity. It hasn't changed. Momentum is always conserved. The difference is, of course, we're going to use the relativistic form of momentum. So put another way, the initial momentum of a system of objects must equal the final momentum of that set of objects after it may interact. Where the initial momentum is just the sum of the momenta of all the initial state objects, and the final momentum is just the sum of the momenta of all the final state objects. This is actually a sum that represents three sums because there's an index here for the vector. So there's an x component of momentum, a y component of momentum, and a z component of momentum. Okay, so it's actually three equations. And as I said, in relativity, we just use that momentum has a new form. P is gamma mu, where u is the velocity. So we have this factor gamma out front for the momentum. But otherwise, it's the same concept. We just conserve momentum in reactions and interactions. Turns out also, the total energy is always conserved in relativity. So along with momentum always being conserved, energy is always conserved, even in inelastic collisions, unlike the kinetic energy. You may recall in introductory physics that kinetic energy was not conserved in inelastic collisions when two objects stick together when they collide, or at least don't elastically scatter. In relativity, energy is always conserved. However, you're considering the total energy, not just the kinetic energy. So that's the kinetic energy plus the rest mass energy. So where does the excess energy go from the kinetic energy in an inelastic collision? So if I have an inelastic collision and kinetic energy is not conserved, if it's less, where does the rest of the energy go? Well, turns out it goes into mass, at least at the particle interaction level. So if you had excess energy beyond what was required for the kinetic energy, the extra energy is going into the mass of the system. So a new feature of relativity in reactions or interactions is that the mass does not need to be conserved in interactions. That is not a conservation law. In introductory physics, the mass was always the same. You might have had a 2 kilogram object scatter off of another object, and it would still 2 kilograms in the final state. In relativity, that doesn't have to be the case. The energy has to be conserved, but not the mass. Let me give you an example of that on the next slide. Let's talk about this concept of binding energy and mass. For example, the mass of the proton is 938.28 MeVs per c squared. In other words, the rest mass energy is 938.28 MeVs, mega electron volts. And the proton is a particle that comprises a nucleus. We're going to learn more about the nucleus later in this course, but you probably already know that the nucleus is comprised of protons and neutrons. The neutron in the nucleus has a mass which is quite similar, a little bit more, 939.57 MeV per c squared. So that if you multiply by c squared, you get 939.57 MeV. Now let's consider the mass of a deuteron, which is a bound state of a proton and neutron. In other words, it is a heavier isotope of hydrogen. It's still got just charge plus E in the nucleus, but you have this extra neutron, so you have a bit more mass in the nucleus. That's an isotope of hydrogen called the, with the electron in the atom, that's called deuterium, but the nucleus itself is called the deuteron. All right. The mass of the deuteron is 1875.63 MeV. Now, let me point out something here. We have the mass of the proton and the mass of the neutron. If I added the mass of the proton, so if I added the 938.28 to the 939.57 of the neutron, I would get a sum of those masses of the free neutron and proton of 1877.85 MeV. But wait a minute, that is larger than the 1875.63 MeV. The difference is 2.22 MeV. Well, what does that mean? Well, what that means is it takes energy to actually break up a bound deuteron in an interaction. The proton and neutron want to stick together. You have to add energy to pull them apart into a free proton and a free neutron. That energy you have to add is called the binding energy of the system. It's being bound by that much energy. You have to add that much energy to break them apart. And we can define it this way. It's the mass of the object separately, individually, minus the mass of the bound system times c squared. And that extra energy that was in the binding energy goes into the mass of the objects when they're separated. And if you added more energy than that, well, then you just get some kinetic energy left over for those final state objects which have been pulled apart. Okay. It turns out, for example, if we take an atomic example, the hydrogen atom, in fact, the mass of the hydrogen atom is 13.6 electron volts, less than that of the electron and the proton separately. So same thing, you have to break apart the atom into a separate proton electron, and the mass will be slightly more in that case. So what we see here is that mass is not necessarily conserved when you have reactions, when you break something apart or you put something together. The total energy must be, and the total momentum must be, but not the mass. All right, let me introduce another concept very similar to the binding energy, and that's called reaction energy. So let's consider a reaction from an initial set of objects to a final set. Right? It doesn't have to be a particle just be broken apart. It could be any reaction we think of. The reaction energy is defined, and we're going to label it Q, as the mass of the initial products minus the mass of the final products times c squared to get it into an energy. As you can see, it's essentially the negative of the binding energy, but that's the reaction energy. If Q is greater than 0, if your reaction releases energy, that reaction is called exothermic. It's the energy released in the reaction, and you may have learned this term in your chemistry classes. If instead it takes energy to make a reaction go, then Q is less than 0, and that's called an endothermic reaction. It requires energy to proceed, just like we had to add energy to break up the deuteron or to break up the hydrogen atom. Let me give you an example. It turns out a free neutron by itself is not stable. It decays. It decays actually into 3 particles: a proton, an electron, that conserves the electric charge, plus and minus, it makes it neutral, and something called an anti-electron neutrino. Actually, the reason that particle is there is quite interesting, and that's a whole story in itself, having to do with particle physics, and that can be something we touch on at the end of this course. But it turns out the neutron must decay into 3 particles. What is the reaction energy as the neutron decays? Well, we take, again, the mass of the initial products minus the mass of the final products times c squared. So I can write basically the rest mass energies. Well, the neutron we learned before was 939.57 MeV in rest mass energy. And that was the only particle in the initial state. I subtract off the mass of the proton in the final state, that's 938.28 MeV. I subtract off the electron in the final state, that has a rest mass energy of 0.511 MeV. And I subtract off the mass of the neutrino, which honestly, we don't know its mass. We do know it has mass though, but we think the mass is less than an electron volt. Very, very tiny. So I'm going to set it to 0 and ignore it. And what I find is the reaction energy is 0.78 MeV. Where does that energy go? It essentially goes into the momentum of the final state objects, the kinetic energy, if you will. So you had some energy left over from the mass of the neutron that went into the mass of the proton and the electron, and in principle the antineutrino. A little bit more energy was left over, and that goes into the kinetic energy or the momentum of the objects moving apart from each other. Okay, so that was an example. Let's do now some examples and some explanation about what to do about calculating the so-called invariant mass. So I want to introduce the concept of invariant mass, because you might think, wait, that's kind of odd. He just told us mass is not conserved. What are you talking about? All right, let me define invariant mass. While the mass does not need to be conserved in interactions, the so-called invariant mass of a system of objects is conserved. It's a Lorentz invariant. Why is it conserved? Well, in one sense, we've already proved that to ourselves using the Lorentz invariant equations. But it's also true because we know that total energy is conserved and total momentum is conserved. And the so-called invariant mass is an expression involving those two quantities. So how do we define these things? Well, we know total energy is conserved, so the energy of the initial state particles is equal to the energy of the final state particles, where that energy in the initial state is the sum of the energies, total energies, of all the initial state particles or objects. And EF is the final energy, the energy of the final state particles or objects, and that's just the sum of the energies, the total energies of each of the final state particles. That's how I get separately the initial energy and the final energy, and energy must be conserved, so those two equal. We also learned that momentum is conserved, the three-dimensional momentum. So the initial momentum equals the final momentum, and there's three components of that, x, y, and z, where the initial momentum is the sum of the momenta of all the initial state objects, and the final state momentum is the sum of the momenta of all the final state objects. What I mean by the invariant mass is this expression here, that the total energy squared minus the total momentum squared times c squared equals m squared c the fourth. That we've learned already is a constant, and here we see it must be a constant because the total energy is conserved and the total momentum is conserved. In other words, that expression here is equal to this one here, where I use the final energy squared minus the final momentum squared. Okay, so that has to be the same constant. So whatever this m squared c the fourth is, this invariant mass I call it, whatever that is initially, even if some of the particles disintegrated and new ones were created, is what it is afterward. Now that may be a little strange to think about, so let me give you another example. Let's do an invariant mass example. So what do we have here? We have an electron and a positron. What is a positron? It turns out it's an anti-electron. It's an antiparticle. Well, we won't really be learning much about that in this course, but the relativistic form of what we'll learn later in this course of quantum mechanics can predict antimatter. So we have an electron and its antimatter partner annihilate with equal and opposite momenta of 1.5 GeV over c. Note the new unit of momentum I've used here. We know that momentum times c is an equal energy unit here, which is 1.55 GeV. So momentum I can call as 1.55 GeV per c, just like I did per c squared for the mass unit. But anyway, I have separately an electron and a positron. They collide and annihilate. The collision produces a new particle, let me move the line, produces a new particle called the J psi. In this reaction we see here. The electron and positron annihilate and make a new particle, just one new particle, even though it's a slash. What is the mass of this new particle? And note that the rest mass energy of the electron is 0.51 MeV. But here I've used GeV, which is a giga electron volt. All right, so let me sketch what's kind of going on here. We have an electron, say, coming in one direction, and it's going to meet an anti-electron, which is positive, and they're going to annihilate. So they're going to collide in the middle and produce this particle called the J psi. So let's write down the momentum of and energy of these objects. So we know that, well, let's give them some labels. Let's call the electron object 1 and the anti-electron, the positron, object 2. So we have that energy 1, well, that should be at least squared. It's momentum squared times c squared plus its mass energy squared. But the momentum P1 times c is 1.55 GeV, giga electron volts. However, I'm going to square that in this expression here. I'm going to be squaring it. Then I have to add to it the rest mass energy squared of the electron. But the electron's rest mass energy in GeV units, I'll write it up above where it says 0.511 MeV, is 0.000511 GeV. Well, if I square that, I get a very tiny number. So effectively in this problem, because the energies are so large, the momentas are so large, we're going to essentially treat that mass is going to 0. And so then that's very easy to see then that E1 is just going to become P1C. Now, as a vector, let's define an axis here. Let's use, let's say white. We'll make this the x-axis horizontally. As a vector, P1 vector would be magnitude P1, the 1.5 GeV, say in the x-hat direction. Okay, what about object 2, the anti-electron, the positron? Well, same thing here. Its momentum in magnitude is 1.55 GeV. That's what the problem said. Its energy, therefore, is 1.55 GeV. But its momentum direction's in the opposite sense. Oops, I'm sorry. P1, sorry, not even P1, it's P2, excuse me. P2 vector is P2, whoops, not one more time, minus P2 in the x-hat direction. Sorry, it took a little bit of time there. Why? Because it's traveling in the negative x direction. So, made this slide a little bit busy here, but we can now calculate, let's say, the mass of this object, this so-called J psi. Remember that mass squared c the fourth equals the total energy squared minus the total momentum times c each quantity squared. Well, what is this going to be? The total energy is E1 plus E2, and each of those energies is going to turn out to be 1.55 GeV. So I'm going to get the sum, which is 3.1 GeV squared, minus the magnitude of the momentum, total momentum squared. But P1 and P2 are in equal and opposite directions, so they cancel when you sum them together. I have 1.55 minus 1.55, so I'm going to be subtracting 0 squared here. So long story short, I'm going to get that mc squared for this object is the sum of 1.55 plus 1.55. It's 3.1 GeV. So that is the mass of this new object called the J psi. All right, so the momenta c, because they're in opposite directions, subtracted from each other. Okay, so that's just an application to solve for two particles annihilating and creating a third new one. And the invariant mass turns out to be the mass of that final object, because we learned that the total momentum is 0, so that object's not moving, so it has no kinetic energy, so this is all rest mass energy, so effectively solve for the mass of this particle called the J psi. even though the electrons themselves in the initial state had their own separate masses, but they had a lot of energy and collided. Okay, maybe just one piece of history. The reason this particle is called the J psi is there was one professor who discovered this particle and called it the J, Sam Ting, on the east coast of the US, and another professor on the west coast, Bert Richter, who called it the psi. They both had separate experiments, whole teams of scientists. They both were awarded the Nobel Prize simultaneously, and so the name was the combination of the two particle names each came up with, just to explain why it's a J/psi. And then the other thing to point out is, although this reaction created the J psi can go the opposite direction. You can decay from a single particle back into an electron and an anti-electron. So you could do the same algebra in reverse as well. And the invariant mass would be inferred from the final state electrons. Okay, that ends this lecture, which has summarized the equations of special relativity, introduced binding energy, reaction energy, and how to use the conservation laws to solve relativistic equations.